In this video, we're going to prove one of the more basic quote-unquote derivative rules when it comes to vector-valued functions of multiple variables. And this is basically the rule that if f of x and g of x are both differentiable at a, then their sum is also differentiable at a. Now to do this, we'll need a few facts. First of all, we'll need the fact that with vector-valued functions, if we have functions f of x and g of x that have limits as x approaches a, then the sum f of x plus g of x, the limit of that will just be the sum of the limits. That's something that we kind of know to be true in the single value case, although if you haven't taken real analysis, you probably haven't seen a proof for that. If you have taken real analysis, the proof is pretty much exactly the same in the vector valued case. But if you haven't taken real analysis, then it would also just be too much to introduce those new proof techniques, so we won't do that here. We have the triangle inequality that says that a plus b, the magnitude of a plus b, is less than or equal to the magnitude of a plus the magnitude of b. And lastly, we're going to use the fact that the partial derivative of a function is the derivative in respect to a single variable. And because that's the case, we're able to apply everything we know from Calc 1 about derivatives of functions to partial derivatives. We need to do a little bit more work if it's not a function of just one variable, if it's rate of change in respect to multiple variables, but the good news is partial derivatives are only in respect to a single variable. So, without further ado, let's go ahead. The first thing I've done is I've just written out by definition, what do we already have? Well, since f of x is differentiable at a, then the limit as x approaches a of f of x minus the linearization of f at a, that's going to be f of a plus the matrix of partial derivatives times the vector x minus a. That all over the magnitude of x minus a, that limit needs to be 0. Similarly, we have that if g of x is differentiable at a, then the limit as x approaches a of g of x minus the linearization of g of x at a divided by the magnitude of x minus a equals 0. Now, we're going to want to write something about the sum f plus g. But to do that, we need to know, when we take f plus g, let's call it h, what's the matrix of partial derivatives going to look like in this case? Well, the good news is that the matrix of partial derivatives for h is going to just be the matrix of partial derivatives of f plus the matrix of partial derivatives for g. And why is that the case? Well, for each element of h, we're just taking the sum of two partial derivatives. And since partial derivatives are derivatives in respect to a single variable, we can use the fact from Calc 1 that this derivative, the derivatives of f of I, or the derivative of f of I in respect to xj plus the derivative of g of I in respect to xj, that's going to be the derivative of f of I plus g of I in respect to xj, which of course is going to be, in this case, with our notation, delta of hi respect to delta xj. So all that is just to tell us that since these are just functions of single variables, we can use our basic Calc 1 addition rule to show that the matrix of partial derivatives for f plus g is just the matrix of partial derivatives for f plus the matrix of partial derivatives for g. So with that, we can consider the limit as x approaches a of, we'll have f of x plus g of x minus the linearization of f of x plus g of x at a. So that'll be f of a plus g of a plus, we'll have the derivative, or the matrix of partial derivatives of f at a plus the matrix of partial derivatives of g g at a all of that times x minus a the magnitude of all that over magnitude of x minus a. We want to show that this limit is going to be 0. Slightly easier said than done. So I'm going to kind of breeze through some of the algebraic manipulations here just for the sake of time. Using just distributing some negatives, rearranging terms, doing some distributive property over here with our matrix addition, all that fun stuff. We can rewrite this as f of x minus f of a minus the derivative of partial derivatives at a times x minus a plus g of x minus g of a minus the derivative of partial derivatives of g at a times x minus a all over x minus a. And the good news here is that we can break this up into two pieces using the triangle inequality. So this will be the limit as x approaches a of, or actually it's not equal to, the triangle inequality is in fact an inequality, so this will be less than or equal to the limit of f of x minus f of a minus the derivative, or the matrix of partial derivatives of f at a times x minus a all over x minus a. It'll be that piece plus the same thing with g. And again, I've sort of done two steps at once here. I broke up the numerator using the triangle inequality, and then I split up that into two fractions by taking each piece of the numerator and dividing it by the norm of x minus a. Okay, so this seems like a lot of work, but the good news is we're just about done. The reason why is because we know the limit of each of these pieces. The limit of this first piece is 0, just from the fact that f of x is differentiable at a. The limit of the second piece is also 0 because, again, it's the limit of, or it's because g of x is differentiable at a. So we have that this limit, or that, yeah, this limit is less than or equal to 0. And that is almost good enough. The one thing we should note is that it's also greater than or equal to 0 because we're just looking at a magnitude here. So there's no way we possibly get negative values. So since the limit is less than or equal to 0 and it's also greater than or equal to 0, thus we have that f of x plus g of x is differentiable at a. And there we go.